Cool, we are back. The goal of this particular set of notes is to explore contractive sequences a little bit farther. So what did we show in the previous video, which is in the content just above this in the notes? We showed that if a sequence x sub n, maybe it was called a sub n, doesn't matter, is contractive, then x sub n is convergent. And let's just recall the definition of contractive. So that's a theorem. Here's a definition. Saying a sequence x sub n is contractive means the following. It means there exists some constant c, a contractive constant, somewhere between 0 and 1, such that for all n in n, absolute x sub n plus 2 minus x sub n plus 1 less than or equal to that constant times absolute x sub n plus 1 minus x sub n. So here's a strategy then. This gives you a way of showing that a sequence converges. It doesn't tell you the limit. But sometimes, especially say if you have a recursive sequence, if you can show that it converges, then you can give the limit a name, and then you can use things about sequences to figure out what the limit has to be. So in the actual step where you prove that the limit is what it should be, there will be no epsilons. You'll just do some algebra, and we'll do exactly that in this set of notes. So here's a sequence. It's defined by a recurrence relation. x1 is equal to 1. X sub n plus 1 is 1/2 x sub n plus 4. And so I guess we can even figure out what, right out the first couple terms of the sequence. So x1 equals 1. x2 will be 1/2 x1 plus 4. So I guess that's 9/2. x3 will be 1/2 x2 plus 4. So that's 9 over 4 plus 4 is 16 over 4 is 25 over 4. x4 is 1/2 x3 plus 4. So that's 25 over 8 plus 4 is 32 over 8. Adding these things together. And maybe it's worth, in order to see what it looks like the limit maybe should be, uh, 7 times 8 is 56. So we see the first couple terms right there. That's not enough to get a guess for the limit. But let's work with this. We don't even need a guess. So let's prove that this sequence is contractive with a constant of 1/2. So let's write down what that means we want to show. So that means we want to show the contractive constant is 1/2. So we want to show that for all n in n, absolute value x sub n plus 2 minus x sub n plus 1 is less than or equal to 1/2. There's the contractive constant c. Absolute value x n plus 1 minus x n. That's what we want to show. So if we want to show that, well, we know how the proof should begin. So let's let little n be a natural number. And let's just start with the left-hand side and see what happens. So we have our occurrence relation for this thing. So let's just use the occurrence relation to expand out everything. X sub n plus 2 is 1/2 x sub n plus 1 plus 4, parentheses for emphasis, minus, parentheses because they're important, x sub n plus 1 is 1/2 x sub n plus 4. And this is just by the definition of xn. Xn is defined by our occurrence relation. That's just using the occurrence relation. And let's just check that out. Let's see what happens. So the first thing that I see is it looks like there's a 4 minus 4. Those will cancel. That'll leave me with xn plus 1 minus xn with a 1/2 next to each. I'll be able to factor out the 1/2. Well, that's good. That actually seems like it will bring me exactly where I need to go. So let's just do those one step at a time. 1/2 x sub n plus 1 minus 1/2 x sub n. And that's just true by canceling. And I guess distributing a negative sign, but that's enough information. Equals 1/2 absolute value x sub n plus 1 minus x sub n. Oh, but wait, that's exactly what we wanted to show. In fact, it's better than we wanted to show. We wanted to show that you could get a less than or equal to there. We have an equal to there. So this is stronger than contractive. It's contractive on the nose. You actually have equality. Thus, x sub n is contractive with contractive constant of 1/2. Next, let's show that it has a limit. This will be automatic. Since, oh, this is way more space than is needed. Since x sub n is contractive, and we've shown that every contractive sequence converges, x sub n converges. So that's not too helpful. It tells you that the limit exists. I would like to know what the limit is. So here's the game that I'll play. So let's let x be the limit. Notice in previous homework / lectures, I would have objected to this claim. This is assuming the limit exists, which you don't often want to do if you want to show that the limit exists, but the sequence converges. So maybe I'll even add this limit. So limit of x sub n exists. Now that I know that the limit exists, that doesn't need an exclamation mark. Now that I know that the limit exists, I can give it a name. Let's call it x. I am now going to use the occurrence relation, namely this occurrence relation. This is true for all n. So let's just write this out. So that means that, let's see, the limit of x sub n plus 1, well, that's the same as the limit of x sub n, which is x. On the other hand, the limit of x sub n plus 1 is the same as the limit of 1/2 x sub n plus 4. We have limit laws, is 1/2 x plus 4. Thus, x is equal to 1/2 x plus 4. We can solve that for x. Solving, let's see, you would subtract the 1/2 x to the other side, you would get 1/2 x equals 4, so x is equal to 8. Thus, the sequence xn converges to 8. So this is a handy strategy. We showed that the sequence is contractive. And that was basically just mechanical. You just needed to check that for every natural number n, some inequality holds. That gave us the conclusion that the sequence has a limit. Once you know a sequence has a limit, you can try to explore what that limit is, in this case, just by doing algebra. You know that the limit exists. Now figure out what it is. Cool. And notice, we didn't have to guess anything. So here's maybe an exercise that'll feel a little bit more motivated. So you know that the square root of 2 is an irrational number. You also know that it's a real number. Here we will come up with a proof that the square root of 2 is a real number. So we'll construct a number whose square is 2 by studying a sequence. So let's let x sub n be a sequence defined by the recurrence relation. x1 is equal to 2. x sub n plus 1 is equal to 1 plus 1 over x sub n plus 1. Let's assume some things. Let's assume x sub n plus 1 is never equal to 0. Because if x sub n plus 1 were ever equal to 0, there wouldn't be an x term of the sequence, which would be bad. Let's assume that x sub n converges. Let's give the limit a name. Let's call it L. Let's also assume that L plus 1 is not equal to 0, so I guess that means L is not equal to negative 1. We'll use some limit laws to now make a conclusion. So, on the one hand, the limit of x sub n plus 1, using this prompt, what is the limit of a subsequence of a convergent sequence? It's the same as the limit of the whole sequence. This is the same thing as the limit of x sub n, that is equal to L. So I feel like this is going in the opposite order of the previous example. On the other hand, the limit of 1 plus 1 over x sub n plus 1, well, we have all the setup that we need to avoid dividing by 0. That's the same as 1 plus 1 over L plus 1 by the algebraic limit laws. Oh, wait, but this is the same as this. This is by the recurrence relation, x sub n plus 1 is equal to 1 plus 1 over x sub n plus 1. We can use that. So, as x sub n plus 1 is equal to 1 plus 1 over x sub n plus 1, it must be that the limit of x sub n plus 1 is equal to 1 plus 1 over x sub n plus 1. Thus, L is equal to 1 plus 1 over L plus 1. That looks like an easy enough equation to solve. Let's solve it. Solving. Well, alright, so you know what I'm going to do. I'll talk through all the steps first. Subtract 1 to the other side, and then cross multiply. That will get rid of the denominator and hopefully make everything easier. L equals 1 plus 1 over L plus 1 becomes, well, let's just write out those two steps. L, so it'll be L minus 1 times L plus 1. L squared minus 1 equals 1. So L squared equals 2. That's interesting. So let's emphasize that. I've highlighted it because that's an important conclusion. Let's read that next prompt. So so that means that this number L, which we know exists because the sequence has a limit, well, we assume the sequence has a limit. If the sequence has a limit, then its limit has the property that its square is 2. So square root of 2 exists. The square root of 2 is a number whose square is 2. So all we need to do now is justify the assumption that x sub n converges to L. How do we show a sequence converges? Well, here's one strategy. Show that this sequence is contractive. And there will be some steps. So let's just go through the steps and then we'll see how it all walks out. So let's first use induction to show that x sub n is greater than 1 for every natural number n. And the reason that this is a good thing to do is because we'll need it in this step, in the next step. So let's try to do that. So base case, when n equals 1, x sub n is equal to x sub 1. X sub 1 is equal to 2, though, because it says so right here. X1 is equal to 2. 2 is greater than 1. Thus, the claim holds when n equals 1. Come on. Inductive step. Let's let n be a natural number and assume xn is greater than 1. We must show xn plus 1 is greater than 1. So let's try to do that. So there's what I want to show. Let's just remember what x sub n plus 1 is. X sub n plus 1 is given right here. I guess really the statement is farther up, but there's the occurrence relation. So let's use that. So x sub n plus 1 is equal to 1 plus 1 over x sub n plus, by the definition of the sequence. And let's remember the goal. There's the goal. So why is this bigger than 1? What do I know? I know that xn is bigger than 1 by the inductive assumption. So xn plus 1 is also bigger than 1. So this whole fraction is 1 divided by a positive number. 1 over a positive number is positive. Right here I see 1 plus a positive number. Yeah, that's bigger than 1. So let's use that. So let's see, by the inductive hypothesis, xn is bigger than 1. So xn plus 1 is bigger than 2, but all I care about is that it's bigger than 0. So 1 over xn plus 1 is bigger than 0. Thus, 1 plus 1 over x sub n plus 1 is bigger than 1. We conclude xn plus 1 is bigger than 0. So by induction, keep your eye on the prize. Xn plus 1 is bigger than 1. Right. We want to show this. You should always make sure that your conclusion lines up with what you need to show. So by induction, we conclude that for all n in n, 1 plus 1 over, nope, that's not what I care about. x sub n is bigger than 1. Next, we will use the recurrence relation and do some algebra to show this. It won't even be that hard. So let's go ahead and do it. Let's show that this happens. It won't be hard, but I might not have given myself enough space. So let's see. By the definition of xn, what do we see? We see that absolute xn plus 2 minus xn is equal to, let's just use the recurrence relation, which says, well, it's written right here. So xn plus 2 minus xn is equal to the absolute value of 1, parentheses for emphasis, plus 1 over xn plus 1 plus 1, close parentheses, minus, so this is xn plus 2, now xn minus xn plus, minus 1 plus 1 over xn plus 1. Well, let's see what we need to do. It looks like 1 minus 1, so the 1's will cancel. And to get these two, I just need to get a common denominator, so let's do that. So this is equal to the absolute value of x sub n plus 1 minus x sub n plus 1 plus 1 all over x sub n plus 1 plus 1 multiplied by x sub n plus 1. Oh, and now we're basically done. So now let's just do, by the definition of xn and algebra. No, it's bad practice. By the definition of xn, we have that so far, which by a little bit more algebra, namely just canceling those ones, and properties of absolute value, is the same thing as absolute value of x sub n minus x sub n plus 1 all over xn plus 1 times xn plus 1, which is the same as what we wanted to wind up with. Cool. So now let's combine these previous two steps. So to show xn is contractive. So let's let n be a natural number. Then by step 4, I know absolute xn plus 2 minus xn plus 1 is equal to absolute value of xn plus 1 minus xn all over xn plus 1 times xn plus 1. So what did we get in step 2? Let's just remind ourselves. In step 2, we found out that xn is bigger than 1 for every natural number. So that means this number is bigger than 1. Something bigger than 1 plus 1 is bigger than 2. Similarly, bigger than 1, bigger than 2. So let's see. By step 2, xn plus 1 is bigger than 2, and xn plus 1 is bigger than 2. So, combining these two together, xn plus 2 minus xn plus 1 is bigger than xn plus 1 minus xn, absolute value pairs, divided by 2 times 2 is 4. Thus, xn is contractive with a contractive constant of 4. So xn converges, and so by step 2, there exists a real number whose square is 2. Great. So this is an example of something you can get out of this seemingly just technical condition that every contractive sequence converges. You can construct a sequence whose limit has to have some special property if that limit exists. If you can show that that limit exists, then there exists some number which has this special property. And there's another advantage to this sort of technique. If you now wanted to approximate the square root of 2, you could by just iterating these instructions. And in fact, we didn't explore what it means to converge exponentially fast, but this sequence will converge very quickly to the square root of 2. Every time you iterate it, well, you know that it's contractive with a constant of 4, so each step will get 4 times closer to what the actual limit is. So the convergence will even be pretty fast. Cool. So I'll get this one uploaded. I hope you enjoy it.